Hello. Uh, Hi. My name's Dr. Simon Smith. I'm one of the lecturers here in the School of Maths and Physics, and yeah, welcome to kind of a virtual offer holder day at Lincoln. So we do these in person and we do them virtually. The idea is that you can meet a couple of the lecturers and one of our students, and then chat, and we can answer any questions you have. So I'm going to talk to you a little bit about the program, about the course and the school, and then after I talk, one of my colleagues, Bart, is going to talk to you, and then after that, you can chat with one of our students later. So, yeah. So let me then tell you a little bit about our school. So we have a full range of mathematics degrees available to study. You can study mathematics, mathematics with physics, mathematics with philosophy, which I think I saw someone signed up for this offer holder day who's looking at maths and philosophy. You can also do mathematics and computer science, and we also have a foundation year. So if someone's A levels don't go quite according to plan, then they can sign up for the foundation year again instead. So there's a full range of degrees. So what that means is that you can enroll on the 3-year BSc. You could then decide that actually you'd rather do the 4-year and maths, so you stay on that, and then you might decide that you want to do a PhD, and you can stay on for that as well. So yeah, there's I suppose a nice structure to the 3-year BSc and the 4-year math, which is that they run exactly the same. So if you enroll on the 3-year course but then decide you want to stay for 4 years instead of 3, this is in fact what I did when I was an undergraduate. I enrolled on a 3-year program and then decided that I couldn't leave mathematics behind, and so I switched to the 4-year. You can do that. The degrees run exactly the same until the end of the 3rd year. So that's quite nice. I think most degrees in the UK, mathematics degrees in the UK, require you to make a choice as to whether you're in the 3rd or 4th year, usually by the middle of the 2nd year. But here you can make that decision relatively late. You can certainly make it in your 3rd year. So also the modules are accredited, as they will be probably at any university you applied for by the Institute of Mathematics and its Applications. Now, maybe I'll just talk a little bit about the university and the school. So, although the university is new, it's a very ambitious university, right? So last year it won Modern University of the Year. It is it's trying to do something different from other universities. We do a lot of small group teaching. There's a lot of contact between the academics and the students. It's a lovely place to study, and one of the things that we really prioritize is the student experience. So what you'll find as you probably look at universities is that that there's various ways in which the universities are ranked. Now, what the government decided to do was to audit the teaching at all universities and fit it within a framework called the Teaching Excellence Framework. And what they did was they gave a score to every university based on how much student support there was, how good their teaching was, things like that. And the highest score you could possibly get is gold. And that's what the University of Lincoln was awarded. And I think that's a reflection of the commitment to your experience that happens here. It's also a highly ranked program, mathematics, right? So it's currently ranked 16th in The Guardian. Yeah, I think, I have taught at quite a few universities in the UK and overseas, and I really feel that the way things are done here is different. There's a lot of lovely interaction between the students and the academics. Like, for example, when I was an undergraduate, I don't think I had a conversation with an academic till I was in my third year. Whereas here, our students are pretty sick of us. They see us all the time. This is the building housing the School of Mathematics and Physics. So this fancy glass entrance, there's a big coffee area at the front and lounge area. And, in here, there's kind of cutting edge computer labs that are open 24 hours a day for all undergraduates. And then there's dedicated spaces for third and fourth years that are also open 24 hours a day. Yeah, it's a lovely building. So the school sits within the College of Science, and inside the College of Science, there's a medical school, computer science, pharmacy, engineering, chemistry. There's a national center for food, which includes like various robotic ways of farming, which got some massive government grant because it's the future of farming, and this is a national center. There's also a School of Life Sciences. Now, if you come here, you will be within the School of Mathematics and Physics, but sitting within the College of Science is quite useful when it comes to projects, or if you want to do undergraduate research experiences, then there's opportunities to do those across other schools within the College of Science. Now, I mentioned that this was a new program, and so there are various advantages to this. So one of those advantages is that the degree here has been designed, and it's been designed with you and your future employability in mind. So, as I mentioned, I've worked at a lot of universities and in mathematics departments, and typically what happens is the following: there's some core subjects, and then people decide, I'd like to teach a course on algebraic topology, so that gets added to the degree, and I'd like to teach a course on nonlinear dynamics, so that gets added. And what slowly happens is the degree gets lots and lots of optional modules, but that creates kind of quite a diffuse degree that isn't necessarily structured for what the current employment climate needs. What happened here is, because we were starting afresh, there was an advisory board formed of leading mathematicians and leaders from industry. This is before they even started hiring academics, and they drew up what they thought the degree should entail. So what that means is that it contains all that you need to really be kind of top of your game when it comes to applying for jobs, right? So, when most students arrive, they arrive really enjoying pure mathematics. They want to study pure mathematics. I'm a pure mathematician. I love pure mathematics. It's so much fun, and I understand that most of you arrive wanting to do that. But there aren't many jobs where you just get to do pure mathematics, right? So you're not going to get a job where, you know, you start on day one and then your boss comes up to you and says, oh, thank goodness you're here. We've been waiting for a mathematician. Here is this integral we would like you to solve, right? That just doesn't happen. What will happen is that your boss will come up to you and say, right, here's some huge complicated mess. Here's a stack of papers. You know, our clients are having this problem and this problem. Can you fix it? And what you will need to do as a technical person is read through this real world problem, turn it into a mathematical problem, and then solve it, and then distribute that solution. And you will probably need to end up discussing technical ideas with non-specialists. So that's exactly how the degree is structured to help you in that task, right? So before becoming an academic, I worked in industry. I worked in finance. I was what's called a quant and a trader. And, you know, this is exactly what happened to me, is you just get a whole bunch of problems to fix that don't seem mathematical in nature to begin with. But your job is to convert them into mathematics, solve them, and then disseminate your solutions. So with that in mind, the degree is balanced between, on the one hand, pure mathematics that teach you to think mathematically, but then applied mathematics that teaches you to apply this mathematical thinking that you've developed to the real world. And then we also have modules in industrial mathematics. We develop your computer skills, because it's impossible to work as a mathematician in a modern environment without needing to use computers, right? So when I worked in industry, I would do lots and lots of mathematics. I was doing stochastic calculus, but then ultimately, you know, what comes out is a you know, a stochastic differential equation. This doesn't have an analytic solution, so you have to write some computer code that will solve that equation. So it's not about being a computer scientist, it's about being a mathematician and getting that final answer. So we will train you on that. And we also, there's a lot of project-based work that will help you with, you know, communicating your ideas to non-specialists. It also helps you when you go for job interviews and things like that. So it's very much a balanced degree that's been designed. It's kind of unique in the UK for that, I think. So some special features: you have research projects from year one. You have a project every single year. These projects will be supervised by an academic, so you'll get lots of contact time with an academic. In your third year, you have a double module that's a project, and that's closely supervised by an academic. Some of those even result in new theorems, like my student this year. My third year project student has proved their own theorem. You know, you could do some amazing things. We train you to use computers as mathematicians. There's an opportunity for a work placement year. This isn't guaranteed, because, you know, you have to apply. It's like applying for a job. A company, you know, will advertise a summer placement position, and then it's up to you to apply. But we have a dedicated team in the College of Science who will help you with that. They will help look over your applications. And yeah, these can be really good. One of my personal tutees just completed theirs at Vodafone, and then at the end of the summer placement, they were offered a job. And Vodafone said they didn't even care what they got in their degree. They were so impressed with the students. So these can be really good, you know, but they are competitive. So you have to apply. And there's also opportunities for summer placements. So how we teach you? We teach you in lectures. That's where you're in a big group and we stand at the front and talk. But then it's very difficult to ask questions in those kind of settings. So we also have personal tutorials. So you have tutorials where you, in your first year, you meet your personal tutor every single week during the term. And there you can ask questions about any of your modules, anything you don't understand. They can help you with, you know, even things that from A level that you really should remember, but you can't remember, you can ask about in there. And then in your second year and third year, you meet your personal tutors less frequently. That's Well, we used to meet every week in those years as well, but then students said they didn't want to meet us that much because they felt settled and happy in the degree. So as part of our responsiveness, we cut those hours slightly. But nevertheless, you still meet your personal tutor regularly. It's especially important if you have any issues that mean you require kind of extra support. Most students don't need it, but sometimes they do. And that's where your relationship with your personal tutor really kicks in. They know you well, they can help support you, they can act as your as your supporter with the university for getting resources that you need. And then when you come to graduate, your personal tutor knows you really well. They've seen you through your whole degree, and so they can write you, wonderfully personalized references. On top of tutorials, you also have problem classes. So for each module that you do, you will have a session with the module coordinator, and they will set you practice problems. And they'll wander around the room, and students will work quietly on the problems, or maybe they'll work in groups quite noisily, and they'll kind of call the lecturer over when they're stuck. The lecturer can kind of give you some guidance. So yeah, so there's kind of the lectures where you see mathematics being done, but then there's these small group sessions where you get to really ask about things you don't understand. Then on top of that, you have all your projects. You have a project in your first year, your second year, your third year. And as I said before, they're supervised by academics. So you get to know those academics really well. And you end up with, then close relationships with academics where they know you, they know your work, they can write about how well you've done in your projects when it comes time for applying for work and needing references. So these kind of personal connections with academics are not something that I suppose you tend to get in universities where there's very, very big departments. We're a small, friendly department where we kind of work closely with our students. And then on top of that, there's seminars and workshops, which where maybe you'll be giving, as a student, you'll be giving kind of delivering some content. It depends on the module, but these are the ways that we tend to teach. So what will your kind of first year look like? Well, you'll have 8 modules. Each of them will be 15 credits. That translates to about 16 hours a week. This is for the BSc in mathematics. Those on joint programs, it will differ slightly. But that translates to about 12 hours of lectures a week, 3 hours of problem-solving classes, and then a 1-hour personal tutorial. So on top of that, you'll be expected to be working on your practice problems again in your own time, and then you come to your personal tutorial or the problem-solving classes with any issues, and then the lecturers will kind of help you work through those. How do we assess you? So again, this is where we're slightly different. We of course use examinations. Everyone uses examinations. They're an important part of our assessment. But we also, in a kind of typical module, only about 60% of the module is the final examination. We also have assignments during the semester that may or may not be timed, and they will typically constitute 40% of your mark for each module. So this way, if you're someone that really doesn't get on well with examinations, you can go into that final examination with kind of up to 40% of your module score in the bag. And that can really help with people that have kind of exam anxiety and things like that. We also have some online assignments. Some modules don't have exams. They have kind of reports like the project modules. or some of the computing modules. So yeah, there's a variety of ways that you're assessed. And yeah, another way is with presentations. These presentations are usually made just to a small panel of academics. So, you know, we're not talking a kind of presentation to your whole year group or anything like that, but it's still important for you to learn how to talk about technical ideas in a way that you can receive feedback for, because you're going to be doing this, you know, when you apply for jobs and things like that. The pastoral care at Lincoln is very strong. It's far and away the best I've ever seen at another university, compared to other universities. We have the personal tutoring system. As I said, it's weekly in the first year. You also will, as I mentioned, really get to know your project supervisors well. If you do a placement year, then there's a placement supervisor that looks after you. Yeah, by the end of your degree, there will be several academics that you know well and can ask for references and things like that. And also several academics that you can go to if, you know, you have personal issues during your degree and you need extra support. So that's an important role that we have within the school. Now, you know, I've mentioned careers. Probably you've already thought about this because you've already applied for your degrees, but I'll just mention it again because sometimes there's people on offer holidays that are deciding between a couple of degrees. And yeah, what I would say is that with a mathematics degree or one of our joint degrees, mathematics and something else, your career prospects are probably unparalleled. You know, mathematics is one of those degrees where it doesn't lead directly to any one career, but almost all technical careers fight over mathematics graduates. So, for example, you know, I worked in finance when I graduated, both as a quant and as a trader, and we would just fight over mathematics graduates with other banks. It's you know, how to phrase this. I suppose if you think about the kinds of things that you learn in your degree, you might learn very specific knowledge, right? So, for example, in an accounting degree, you're learning very specific information about accounting. If you do an accounting degree and then you decide you don't want to be an accountant, then you then have on your CV a bit of a job arguing why you're, you know, you did an accounting degree, but you no longer want to do that, right? If you do a mathematics degree, no accountancy firm is going to look at a mathematics degree and be like, oh, they didn't do an accounting degree. No. You should also bear in mind that in a mathematics degree, you learn to think very differently to other people. It's called mathematical thinking. It essentially involves thinking very creatively in an abstract setting, and then to generate ideas, and then thinking very precisely to analyze each of them to see which one will work. And then when you find one that works, thinking again very analytically to kind of power your way through the problem. This is not really something that is easy to learn using any other subject. So thinking mathematically is something that's developed in pure mathematics modules. It's very, very difficult to teach. It takes a whole mathematics degree to teach. The kinds of specific knowledge that you need for a job, you can teach quite quickly. So, for example, when I got my job in finance, I hadn't taken any modules in finance or anything. And I was told, well, just, you know, read these 3 books on finance. And then I was given a couple of months, and then that was it. I started. And later, when I was in charge of hiring people, that was exactly our policy. We would hire mathematicians, physicists, philosophers, people that are used to thinking abstractly and creatively, and then we would just give them some books and get them to teach themselves finance rapidly, and we'd send them on some quick courses. So yeah, this means that with a mathematics degree, you really have a lot of options for your future career. So obviously there's finance, obviously there's IT. Probably you know that Google was started by a mathematician and a computer scientist. Mathematics is deeply embedded in computer science. Obviously there's education, you're used to that. There's industry. One of my former students went on a hackathon where she didn't realize, but Siemens representatives were embedded there watching people, and she got offered a job there. No interview needed or anything. They were so impressed with her, they just offered her a job on the back of it, and she's now an engineer at Siemens. There's academia, which of course you know. Defense, many people don't realize that a huge employer of pure mathematicians is GCHQ, which is our kind of, I don't know, cryptography, kind of spying institution. The NSA, which is America's equivalent, is, I think, the largest employer of pure mathematicians on Earth. Yes, if you've ever read anything about breaking the Enigma code in World War II, then that's the kind of thing that mathematicians do. NHS also employs lots of mathematicians for data mining. There's a lot of mathematics that goes into healthcare. And then there's another one, operational research, that people don't necessarily think about. And it's essentially helping companies optimize their operations. So if you think about Tesco's, they've got some groceries, they've got some lorries, they've got some drivers, they've got lots of stores. They want to get their groceries into the stores using the fewest number of drivers and driving the fewest number of miles. And this is a very difficult problem, and it's called operational research. It employs vast numbers of mathematicians. It always has a very, very high job satisfaction rate. So when you're looking at kind of careers with happy employees, it tends to rank quite highly. So yeah, that's another big employer of mathematicians. Maybe I'll just kind of talk very briefly for the last couple of minutes about some of our recent graduates. So Laura now works in kind of, I guess you could call it big data, using mathematics to spot patterns in the data that Boots get from their loyalty card scheme. Yeah, those loyalty cards that you use in various stores have teams of mathematicians behind them mining the data. Reese works in finance as a credit risk analyst for Santander. So yeah, he's doing very well. Peter did maths and computer science, and so he's now a developer. Brittany did, she enrolled and wanted to be a teacher. So then after she graduated with a mathematics degree, she went to Cambridge to train to be a teacher, and is now a high school maths teacher. Sophie was one of my project students. She was the student I mentioned earlier, that she kind of went to a hackathon and was one of only a few people selected by Siemens onto their kind of accelerated program. So that's where she is now. And yeah, so you can kind of see from that, I know I kind of clicked through quickly, but you can see from that just some of the things that our graduates have gone on to do. So yeah, thank you for your time. If you've got any questions, then you can ask away or put them in the chat. Yeah, maybe I'll wait a minute, see if anyone has any questions, and if not, then we'll move on to the next thing. Well, yeah, as there's no questions, I suppose if you've got questions, then you can ask me at the end, or also at the end there'll be one of our students will be chatting with you, and so you can ask her. So yeah, if there's no questions, then I suppose I'll hand you over to another one of our lecturers, Bart, who's going to give you a kind of a sample lecture, so you can sort of see some of the mathematics that you might encounter as part of your degree. So Bart, are you there? Hi, Bart.
Hi, Simon. Thank you.
Yeah.
Yes, welcome everyone. So I'm Bart Vasselaars. I'm a senior lecturer at the School of Maths and Physics, and I'll talk a bit about a sample lecture. So the sample lecture is actually based on a third-year student project, and I'll discuss some of the maths involved and how this plays a role in this project. So what I'm considering is the following. It's called Buffon's needle. And Buffon's needle, you first is a very simple experiment. You take a needle and measure its length L. So you have a picture of a needle. Then you draw equally spaced lines on a flat table, and they are separated by a distance d, which is twice the length of the needle. So here they indicate by those red lines. So the distance d between them. And what you do then, you just toss the needle on the table and see whether or not it crosses a line or not. Yeah? So in this particular case, you can see the needle crosses one of those lines. So it's a cross, and then you do it many times, this experiment. So in this case, it doesn't cross it. And what you then calculate is the total number of throws, so how many times you throw the needle, and how many times of those throws it crosses. And then it turns out that if you divide the number of throws divided by the number of crossings, you get pi. Yeah. So this is an example. So here I have 36 throws. So you see all those needles falling on the table. Then I try to see which of them actually touches one of those lines. And you can see 11 of them crosses a line. Yeah? So they are now indicated in blue. So 11 out of 36. And then I can actually calculate the approximation for pi. So in this case, the number of throws is 36 divided by 11, which is about 3.27. In this case, it's relatively close to pi, which, as you know, is 3.14. Yeah? So obviously, the big question is, why does this work? Yeah? And this we can actually answer using some mathematics. So for this, we need elements from geometry. We have the orientation and position of the needle. We need something from calculus and probability and statistics. So how does the random element come into this? So in this talk, I won't go very deep in all the things because otherwise you won't have the background knowledge. But in this case, this problem should be accessible. So first we have to look at the factors actually that determine crossing. Obviously, it is the distance between the lines. And for simplicity, I just take the d, the distance between the two lines, equal to 2. And the length of the needle. Again, to simplify things, I just set the length of the needle to 1. So I rescale everything that the length of the needle is 1. And obviously what matters, you might guess that what matters, whether or not it crosses the line, is actually the angle which the needle is dropped. And obviously the position of the needle. And a good reference point will be the middle of the needle. So that's what we consider. And then let us introduce our new variable. In this case, it will be z. And I define z to be the distance between the midpoint of the needle to the nearest horizontal line. And so here you can see z on the right-hand side. So that's this distance. And the length of the needle is 1. So the half the length between the midpoint and one of the ends will be a half. Okay, now I'll want to introduce yet another variable, which is called theta, and theta here is the acute angle between the needle and the dashed line. So in this case, theta can vary all the way between 0. So for theta is 0, the needle would be parallel to one of those horizontal lines, or all the way to pi over 2, where it would be perpendicular to one of those horizontal lines. Yeah. So when I actually throw a needle, then I can specify what range of z it will be. Now, if I throw the needle and it lands, the midpoint lands exactly one of those lines, z will be equal to 0. So that's my lower limit. And I also have an upper limit when the needle ends exactly in the middle between two of those horizontal lines. And then the midpoint would be a distance z of d over 2 separated from either line. So that is basically the range of the z. If it goes lower, it is actually closer to the lower horizontal line. So it actually becomes smaller than d over 2. Yeah? So those are the limits for z. And as I discussed, the limits for theta, so this angle of the acute angle is between 0 when it's parallel to one of the horizontal lines, and pi over 2 when it's perpendicular to one of those lines. So then we actually have to come up with criteria when it actually crosses the needle, one of the horizontal lines. And for this, it makes sense to draw a circle around the midpoint. Yeah? So that's what I did here. In the blue is the circle around the midpoint with the same radius as half the length of the needle. So in this case, the radius would be half. And you can see now in this dashed red line, if the needle happens to fall with the angle corresponding to that section of the circle, it will actually hit one of those horizontal lines. Yeah? So that is in that area we have a crossing. So how do we determine that? Now, for this, I first introduce a new variable, x, and x in this case will be the distance from the top of the needle till the dashed line. The dashed line corresponds to the midpoint of the needle. That is parallel to one of the horizontal lines. Yeah? Now, the condition for crossing is then when this distance x between the top of the needle and this midpoint is larger than z between the midpoint and the top of and this horizontal line. Yeah, then it crosses the horizontal line. Now, obviously, I have introduced a new variable, but this variable x is actually not independent of the other variables. We can actually express it in terms of theta, and you might already have seen it. There's a little triangle that we can discern here. So let me zoom in, and so you can see we can replace that by a blue triangle. So x, as I said, is between the top of the needle and the dashed line. So that's x. They have the angle theta. And from trigonometry, you might remember that we have this rule SOH-CAH-TOA. In particular, the first word means sine of theta is opposite divided by a hypotenuse. So opposite side here will be equal to x. And the hypotenuse, in this case, will be half the length of the needle. Since I set the needle length equal to 1, half the length will be equal to half. Yeah? So I have sine of theta is x over a half. Or if I bring the half to the other side of this equation, then I have x is a half times sine theta. And so that way we can get rid of x. And then this condition of crossing transforms, so x, the distance x has to be larger than z in order for the needle to cross one of those horizontal lines. It can be replaced by half sine theta. It's larger than z. Yeah? So now we can actually make a schematic scheme of this experiment. So when we throw a needle, we actually choose a value for z. So the distance between the midpoint of the needle and the horizontal line. And I discussed it should be between 0 and d of 2. And we choose a value of theta between 0 and pi over 2. So those are all the possible outcomes from the experiments. And then I have this condition for crossing. This is a half sine theta should be larger than z. Now for z is equal to 0, the needle is already exactly on the horizontal line. So that is already a condition for crossing. So we basically see that the x-axis includes the crossing area. But if I now draw this half sine theta, or z is a half sine theta, I get this black line, and just underneath the black line is the red area. So if a needle lands in this red area, so the variables corresponding to orientation of the needle correspond to the area in the shaded red, then I know it has crossed one of the horizontal lines. Yeah? So we have a crossing. So what we want to do now? We actually have to calculate those areas. Yeah? Because that will determine the probability of the needle crossing the line. So I can state that as following. So the probability of needle intersects is all cases where needle crosses, so that's this red area, divided by all the possible cases, and that will be the area of the rectangle, because those are all the possible outcomes when I just throw a needle. Yeah? So now let's calculate those individual areas. Now the area of the rectangle is easy. It's just the width times the height. It's d over 2 times pi over 2. So this pi times d over 4. And then I want to calculate the area of the curve. So this is the integral from 0 to pi over 2. And so I integrate from 0 theta 0 to pi over 2. Those are the valid outcomes for the angle of this half sine theta function. Now, you might remember that the integral of the sine of theta is cosine theta multiplied by a minus sign, so minus cosine theta times a half, and I have the limits of pi over 2 and 0, so I have minus a half cosine pi over 2 minus a half cosine of 0. Now, the cosine of pi over 2 is just 0, the cosine of 0 is equal to 1. So the first term becomes equal to 0, and the second term is equal to a half. A minus and minus is plus, so it's a half. So basically, the area under this curve is just a half in these units. Yeah. So now they come back to the probability that the needle intersects. You see that's the area under the curve divided by the area of the rectangle. So it's a half divided by pi times d over 4. And if I take d is equal to 2, so twice the spacing, twice the needle length, we can see that this probability is just equal to 1 over pi. So we can already see where we're getting at. So the probability of the needle intersects is 1 over pi. So we just invert this relationship. The left-hand side and the right-hand side. Number of sections divided by number of throws. So that becomes number of throws divided by number of sections is equal to pi. Yeah? So using this elements from calculus and probability, we see we can determine pi, get an estimate of pi by just throwing a needle many times and calculating the number of intersections. Now, you can do this in practice, but you'll find that after a while you might get tired of throwing all those needles and counting every time whether or not it crosses. So for this occasion, you can also do actually simulations on the computer. Yeah? So a computer simulation where you mimic the throwing of a needle on the table. And a simulation in general have various benefits. You can save time and money, and it also excludes some human error. And a simulation are actually very common in lots of practical applications as well. Some situation that Simon also discussed, like in finance, you have simulation of how a stock might change over time, or an engineering problem. You might want to simulate some equipment, etc. So in this case, I discussed the Monte Carlo simulation. Monte Carlo simulation basically means that you use some kind of random number. So random numbers, say, similar to throwing a dice. If you throw a dice, 6-sided dice, you get either result 1, 2, 3, 4, 5, or 6 in equal proportions. Now, in a computer, you can do something similar. You can generate, for example, a random angle. So in this Biffle needle case, we basically need to generate random numbers to determine the position of the needle on the table, and also the orientation of the needle, so a random angle theta. Yeah? And the student that did this project basically did the Monte Carlo simulation in Python, because it's relatively straightforward programming language where you can also visualize things. So it just generates lots of random numbers. Then using those random numbers, you can actually plot the needle on the board. And then using the orientation of the needle, you can then determine whether or not it crosses one of those horizontal lines. Yeah? So the student, he did this experiment many times, and you can already see, the results are basically given in this table. So you can see the first experiments he did was just 10 needles. From that, he determined that 4 of them crossed the line. Now 10 over 4 is 2.5, so that will be the approximation for pi. You can see the percentage error in this case is about 20%. Then he did it 10 times as many, so 100 times. In that case, there were 28 crossings. We got an approximation for pi is 3.57. The error is about 14%. And so he increased the number of experiments every time by a factor of 10. And you can see 100,000 times. If you do that by hand, it will take your ages. And in this case, the estimate for pi is about 3.12, which is less than 1% difference from the actual value of pi. So the more experiments you get, the closer you get to the real value of pi. So that is one way of doing it. But you also considered different situations. So you can also consider the case of a long needle. So I won't go into detail, but for long needle, the probability changes, and you have to do some slightly different calculation for the area when it crosses. It involves an arc sign, but it basically still depends on the ratio of D over L. So the distance between the horizontal lines and the length of the needle. And this is an expression where P is the probability of crossing. So that is a slightly different expression. You can also consider a square grid. So instead of only having horizontal lines, you can also have vertical lines. And then when it crosses either of those lines, in this case it's still for a short needle, then the expression becomes this: pi, approximation for pi is 4 times the length of the needle times the distance between the lines minus L squared divided by the probability and D squared as well. So here you can actually see the resulting experiments. So those are 1,000 drops. So the short needle, I already gave you an example. The long needle, it becomes more and more rare that the needle actually doesn't cross the line. They have to be really almost like parallel to one of those horizontal lines in order not to hit it. And then finally, I also have an example for a square grid. So he actually used those results to verify those analytical calculations that you can do as well. Yeah. Okay, so this was basically a short introduction of this student project. I'm not sure if there are any questions about this. Okay, if there are no questions, then I'll pass this presentation to our student ambassador, Leah. Was happy to answer any questions you might have about the course.
Hi, yeah, so I'm a third-year mathematics and philosophy student studying at the University of Lincoln. If you have any questions, I'm here to answer them. If you don't, then I will talk about some of my top tips for living in Lincoln. I'll just wait a few minutes and see if there's any questions. If not, then I will speak about Lincoln University. So I'll just get cracking with some of the top tips then. So for me, some of the top tips for living in Lincoln and for Lincoln University would be to definitely climb Steep Hill and visit the cathedral at least once. It is an absolute nightmare to walk up the hill. It is one of the steepest hills in Britain, but is completely worth it when you get to the top, and there's a really nice ice cream shop at the top. that's always something that's quite nice to do, especially in summer. So I would highly recommend doing that. One of the other tips that I would give for first years moving in is to bring a door stop with you to keep your door propped open in those first few weeks that you are living in Lincoln. It's always a really good way to meet new friends, let them know that your door's open, that they can come and chat to you, anything like that. So that's always really, really nice to be able to do. So they're some of my top tips, probably the best two I can come up with. There still doesn't seem to be any questions. So yeah, that's kind of, there's no more questions, it doesn't seem to be. Something else about living in Lincoln is that it is very, very cold, so I would recommend wrapping up warm. If there are any questions potentially that you can think of later on, not just now, but at some point in the future, then to email sciencemarketing@lincoln.ac.uk. If you have any further questions, then feel free to email them. They're pretty good at responding. They'll be able to respond to your email within 5 working days usually. So if not, then thank you so much for joining our presentation, and we hope to see you in September.